Problems 23 and 24. The following information applies to questions 23 and 24. A 100 kg astronaut carries a launcher loaded with a 10 kg bowling ball. The launcher and the astronaut's spacesuit have negligible mass. The astronaut discovers that firing the launcher results in the ball moving away from her at a relative speed of 50 meters per second. Question 23. What is the impulse delivered to the astronaut when firing the launcher? Solution. Here we can use information for two facts. First fact is that relative speed was 50 meters per second. And second fact is momentum conservation. Let's convert these facts to equations. Suppose that velocity of astronaut is going to the left and the velocity for bowling ball is going to the right, and both are positive. It means that we have two equations: delta V1, which is speed of astronaut, plus delta V2, which is speed of launcher, equal V, 50 meters per second. And also we have m1 delta V1 equal m2 delta V2, which is momentum conservation. And from these two equations we can find what is delta V1 and what is delta V2. We have delta V1 equal V multiplied by m2 over m1 plus m2, and delta V2 is symmetrical. And now we can count what is delta P, what is the impulse delivered to the astronaut or either launcher. This is the result for delta P. That's equal V multiplied by m1 m2 over m1 plus m2, which is 455 Newton by second. That's the answer A. Question 24. The astronaut in the previous situation is now moving at 10 meters per second as measured in a certain frame of reference. She wishes to fire the launcher so that her velocity turns through as large angle as possible in this frame of reference. What is this maximum angle? Hint: a diagram may be useful. Solution. Let's draw the diagram. Suppose that Pi is initial impulse of astronaut, and suppose that J is impulse given to this astronaut by the launcher. This impulse could be in any direction, so it means that the vector will cycle the circle, and the final impulse Pf could be vector which is ending on this circle from initial point. And from this geometry we can tell that the maximum angle could be possible when final impulse and delivered impulse have angle 90 degrees. In that case angle theta has a maximum value. On this picture we can find that sin theta equal J over Pi, which is delta P from previous problem, divided by mass 100 kg multiplied by speed 10 meters per second. So finally we have sin theta equal 0.455, or theta equal around 30.0 degrees, which is correct answer D. Problem number 25. A block with mass m is released from rest at the top of a frictionless ramp. The block starts at a height h1 above the base of the ramp, slides down the ramp, and then upper second ramp. The coefficient of kinetic friction between the block and the second ramp is nil. If both ramps make an angle of theta with the horizontal, to what height h2 above the base of the second ramp will the block rise? Solution. Let's draw the picture. To solve this problem, we can use work energy theorem. It means that initial potential energy of this block equal to final potential energy of this block plus the work done by force of friction. And because first ramp is frictionless, so we can use just work done on the second ramp. And we have this equation. We have mgh1, which is initial potential energy, equal to mgh2, which is final potential energy, plus mu mg cosine theta, where mg cosine theta is normal force, and multiplied by mu, that's the force of friction, and multiplied by h2 over sine theta, which is distance. And from this formula we can find what is h2. That will be this expression, which is answer A, correct one.